All right, let's look at this one. We're going to integrate square root 4x plus 5. All right, so this is not just a power function. There's some terms inside the square root. And so whenever we're seeing kind of an outer function and an inner function, we should start to think substitution rule, the opposite of chain rule. So that's what we're seeing here. Is there's this square root, it's an outer function, and then we have 4x plus 5 that's inside of it. Well, how are we going to integrate this? First thing we normally do with square root functions, or root functions in general, is rewrite them as a power function. And this is going to be helpful because we're going to rewrite this as a power function, and that's going to really emphasize how we're going to pick u. So rewriting this, it'll be 4x plus 5 all raised to the 1/2 power. And so we see a nice set of parentheses. There's something complicated inside, 4x plus 5. That's what we're going to pick for u. So step 1, we're going to choose u to be 4x plus 5. All right. Not too bad. Now, once we choose u, our hand is forced. We have to calculate du. So derivative of 4x plus 5 is 4, and then we multiply by dx. All right. So now we look at our original integral here, this 4x plus 5 raised to the 1/2 dx. And this is where things, we've seen enough examples now, where things don't always match up perfectly. And that's what we're going to see in this example. So first of all, this 4x plus 5, kind of by our choice, is going to match up perfectly. That's going to be our u, kind of by design. Now, what do we have? What's left over? Let's start filling the pieces in. We want to substitute everything in. And let's see here. Leave a little space right here. So let's start substituting things in. So this 4x plus 5 is going to become u, and then that'll be raised to the 1/2. All right, so far that's not too bad. Now if we look, what do we have left? We have this differential dx that we need to convert. We can't have a dx. It has to switch some way into du. Now if we look at what we have calculated for du, it's not such a perfect match. We have this 4 here. So yeah, we do have a dx. So the dx's match, but there's this extra 4 that doesn't show up in the original integral. So how can we handle this 4? There's this extra constant here. What can we do? So our strategy is we're going to solve for what we do have. We're going to solve for dx. So we're going to solve for what we have. All right, so let's get our dx here. And how can we solve for dx? Well, multiply both sides, or divide both sides by 4, or multiply both sides by 1/4. So if we do that, we get 1/4 times du. And that's going to be our dx. So essentially, we're dividing both sides here by 4. And so to switch over this dx, we need to know, well, what is dx equal to? And here it is, 1/4 times du. So this is what we're going to plug in up here. So what we're seeing in this example is when our differential it's not a perfect match with our differential. So we had only a dx here, and it wasn't a perfect match with what we calculated for du over here. In our previous examples, let's just take a look. Everything matched up nicely, and that was on purpose, kind of, because they were the first few examples we're looking at. So here, our original integral had a 3x squared dx, and that matched up perfectly with what we calculated for du. That's very special. It doesn't normally happen like that. It was a perfect match, so we didn't have to worry too much about that. Going back to the other example, we had 2x times dx kind of left over, and that matched up perfectly with what we calculated for our differential. Again, that does not normally happen. The reason why it happened here is because this was the second example we looked at. So we kind of made that nice, but it doesn't always happen. And then I think even in the first example, something similar. So this is normally kind of what happens with substitution rule, is the differential takes a little bit of work. So we solve for what we have. We solve for those leftover terms. In this case, the dx. So the dx was left. We solve for whatever leftover terms we have, so solve for dx. And this dx now is going to become 1 over 4 times du. So we put that into our integral. And so now, after plugging all of this in, we have the integral of u raised to the 1/2 times 1 over 4 du. And this is just a power function with a constant multiple. And it's all in terms of u now. So it's du and it's u here. So this is an integral we can do. All right. So this 1 over 4 is a constant multiple. So I'm just going to put that first. And then I'm going to work on getting the antiderivative of this u to the 1/2. So the variable is u. I add 1 to the exponent, takes me up to 3/2. Take this new exponent, flip it, put it in front of the u. So 2/3 goes in front. And then plus c. And that's step 3. That's actually getting the antiderivative. And then step 4, we're just about done. The only thing we need to do is convert back to x. And while we're at it, simplify if you can. So 1 over 4 times 2/3, there's a 2 here, and then there's a couple 2's in this 4. So some of the 2's cancel, and we end up with 1 over 6. And then instead of u, we're going to convert back. So it'll be 4x plus 5 raised to the 3/2 power. And then our plus c. And that's step 4, the last step. Get back to the original variable. And there we go. We have our antiderivative. And if we wanted to check this, we could use the general power rule to check our answer. This is just chain rule. We could use this to help check our answer. And you should get back right where you started. All right. It really comes down to practice. So we're just going to keep trying some examples here. And each time, hopefully, talk a little bit about slightly different ways on little strategies and techniques and tips and thought processes of how to actually choose u. That's generally the hardest part, is how do we calculate u?